Everyone, I'm Alex Biamkama. Today I want to take you through colligative properties. Colligative properties. Take an example considering the solution A containing pure solvent. On heating the solvent, it will have to vaporize and produce vapor. The vapor exerts a pressure called a force called vapor pressure. And for pure solvent, no solute added. The boiling occurs when vapor pressure is equal to atmospheric pressure. Another example can be consider another solution where, for this case, a non-volatile solute is added. Let's say 2 grams of non-volatile solute was added to a pure solvent. For this case, the vapor will have to reduce. Vapor pressure also reduces on heating this, and to equalize the vapor pressure with the atmospheric pressure, more heat must be applied. Another can be C. Let's consider container C. For this case, 4 grams of a non-volatile solute added. Vapor pressure reduces further. Vapor pressure here reduces further. Vapor reduces further. And for you to equalize atmospheric pressure with the vapor pressure of the solution, more heat must be applied. And when a non-volatile solute is added to a pure solvent, this escaping tendency of the solvent molecules into the vapor phase is lowered, hence lowering of vapor pressure of the solution. To raise this low vapor pressure so that it becomes equal to the atmospheric pressure, a higher temperature is needed for boiling to occur, hence an increase or elevation in boiling point of the solution. Consider container A, containing pure solvent A. The freezing point is 14 degrees Celsius. And when you add on addition of a non-volatile solute, these non-volatile solutes prevents the solvent molecules from coming closer. So therefore, freezing point is, for instance, 10 degrees Celsius. Freezing point has reduced, therefore freezing point reduces depression in freezing point. Take another solution. Let's say solution P. For this case, they are separated by semi-permeable membrane. The solution is separated by semi-permeable membrane. For this case, we have pure solvent this side, pure solvent. Here, no movement of solvent molecules from either sides. Another container Q contains a concentrated solution, pure solvent plus 4 grams of non-volatile solute, a semi-permeable membrane. These arrows indicate the movement of solvent molecules. Pure solvent, meaning that the pure solvent moves from the solvent side to the concentrated solution, and therefore the level of the solvent molecules will have to reduce. Another container R of a more a more concentrated solution, pure solvent plus let's say 8 grams of non-volatile solute, separated by a semi-permeable membrane from a pure solvent. For this case, more solvent molecules move to this concentrated solution, and therefore the level of the solvent molecules reduces further. The movement of solvent molecules, from a region of concentrated solution, from a region of low concentrated solution to a high concentrated solution across a semi-permeable membrane is called osmosis. The minimum external pressure which must be applied to the solution to prevent osmosis from taking place is called osmotic pressure. And the higher the osmosis, the higher the osmotic pressure. The physical property is osmotic pressure, and it depends on the number of particles, hence colligative property. Therefore, lowering of vapor pressure. 2. Elevation of boiling point. 3. Depletion of freezing point. 4. Osmotic pressure. All depend on the number of non-volatile solute particles added to this dilute solution, but not on the chemical nature. And in conclusion, colligative properties are the physical behavior of a dilute solution which depends on the number of non-volatile solute particles, but not on the chemical nature of the solute. Thank you for watching.